Hi, my name is Shiming Song. I'm a sophomore in electrical engineering. I'm working with Professor David Blau and graduate student Yanpo Chen. The research project I did over the summer is designs of low current voltage dividers. So let's take a look at the background, the outline of this presentation. So in the introduction section, I'm going to talk about the reason why we need this research project and what we're looking for and the actual experiment I did. And then we go through the designs I looked at over the summer. And then there's the work that remains to be done. And then we conclude the presentation. So first, let's take a look at the background of this research. So here's the traditional design of a voltage divider. The problem with this is it has a steady state current and can be very high. So if we want this to be lower, we need a higher resistance. Say if we want a 10 picoamp current, it's going to be 100 gigaohm, which means several millimeter squared area, which is too big to be implemented. So the goal of this research is basically to solve this conflict between the current and the area. So we have several different designs for this goal. And let's look at the criteria before we actually take a look at the designs. So say what do we want? So we want low current and high accuracy and a small area and high robustness, which I will explain later. So let's take a look at the experiment I actually did. So the experiment is very easy. It's dividing by the same number for different designs, and we compare the results from simulation. So let's take a look at the first design, which is a traditional design as a reference. So here's the diagram I'm using for the design. It's very easy, and it's the same as what we talked about before. So the testing result is here. The current level is around 100 picoamp, which is acceptable, and the area is about 10 millimeter squared, which is too big. It's almost as big as a single chip, and the accuracy is very good. It doesn't have any problem with the output. The output is just stable as what we want, and the Monte Carlo simulation result is as presented. So this is a simulation we use to see how the circuit behaves if some of the components are not manufactured exactly the same as what we designed, which happens very frequently. And I deleted all the numbers to protect the lab technology, but the only thing we need is a standard deviation, which is not that dangerous. So standard deviation is 200 microvolt, which is acceptable. So to summarize this design, we have very good accuracy, we have good robustness, but the disadvantage is not realizable because of the huge area. So to actually make this, we need the area to be smaller. So then we have to treat off some current to make the current higher, which is not desirable either. So then we have a better design, which is the off-state MOS. As we can see on the slide, we use the MOSFET, which is the very popular switch in an integrated circuit. And presumably most people know that when the MOSFET are off, they're not really off. They're still conducting. But the currents are very low, which is exactly desirable for this design. So we just turn off all the MOSFETs and put them in series and using exactly the same network as the resistor voltage dividers. So let's see the test results. The current is smaller than 1 picoamp, usually several hundred femtoamp, which is desirable. And the area is around 1,000 micro squared, which is 1,000 times smaller than the reference. And the accuracy is very good, so it's the same, it's very stable and accurate. But the smaller MOSFETs are very sensitive to variation. So to summarize this design, the advantage is very small, it's very accurate, but it's very sensitive to variation. Some variation might make this just not working. So, and the potential improvement is just trade off some area. So we can solve this by making the switches bigger, so then the mismatch is not that big deal. So here's the plot I generated, so as a reference. So again, I'm not supposed to give numbers. So the sigma means how much the circuit is affected when a variation happens, and the area is how much we need to get that level. So as we see, we can increase the area and use this plot as a reference when we want to use this design. And here comes the last design, is a switched capacitor network. So here's an example dividing by 6 design. It's a little bit trickier to work with, but it can be very accurate and very low power. So the black capacitors are the actually operating capacitors. They switch from series to parallel, and the charge are carried like in when the switch is switching, and the red one's the decap, which we're taking the output from. So and here's a fancier design for dividing by 7. So we only need 5 capacitors to divide by 7. But I'm not going to expand this further because of the time limit. So here's the test result for a switch capacitor network. The current level is several picoamp range, which is pretty low. And the area is several thousands of micrometer squared, which is a little bit bigger than MOSFETs, but it's fine. And the accuracy is not as good. The output is oscillating, so it's not stable anymore. But the oscillation can be suppressed as well, as we can see in the 2 plots below. The one on the left is the original, and the one on the right is after some technique like using bigger capacitors and smaller switches and dummy switches, which I'm going to talk about later. And here's the multicolor distribution, and the standard deviation is 400 microvolt, which is acceptable. And to summarize this, the advantage is robust and it's flexible because sometimes it can deliver a little bit of power instead of just no power in the offset MOSFETs. And the disadvantage is that it has a larger area and oscillating output and very high current spikes because the circuit is switching. And when it's switching, there are a lot of switches, so the current can be spiking in some very short time. And to improve this, we need some dummy switches and some current limit technique. So to see the dummy switches, we can see from the schematic that we put 2 smaller switches on each side of the main switch we're using. So when the main switch turns off, there are some charge that escape from the main switch to the capacitor. That is going to affect the output. So after we putting the 2 smaller switches, they absorb the charge that escapes from the main switch, so that the output is not that much affected. So here's the result we get after putting on dummy switches. So we can see it's very flat most of the time. And there might be a spike, but the spike is very short. It's only like microsecond range. So it's still acceptable. And here comes the future work. So the current spike limiting is still a problem that remains to be solved. And so since I'm not supposed to give much about the number, I can use the normalized version. So here's say the original current is 100x, which is too high. And the technique is stack transistors. So we put some resistance between the actual source and the whole capacitor circuit. And we put a big capacitor as the virtual source to charge up all the capacitors in the switch capacitor circuit. And the result we're getting is as follows. So the red curve is the output voltage after we're putting the stack transistors. So it's only 0.1% error, so it's very good. And the current can be limited to 1x, which is acceptable. And the other solution would be the sub-threshold design, which is using off-state MOS. So we are using leakage current again. But this is still desirable because the current can be limited to very low. It's only 0.01x current. So, but this design is not verified completely yet, so I still need to work on this. And here's another thing I have in mind is the switch capacitor circuit unifying. So basically, as we can see, divided by 5, divided by 6, and 7, 8 are very similar. So there should be some way to unify them to a voltage divider that's very flexible. So I need to implement this later. So then we come to a conclusion. So the conclusion to this research project is that the resistor design is still the most robust to variations, but it's not realizable. And the offset MOS is the easiest to implement, but the area and the current are both acceptable, but they are very weak when the variations are present. And the switch capacitor is not much bigger than the MOS design, but the current can be very low, and they have the potential to be more robust. So here, so at the end of the presentation, I want to thank Professor David Blau, Professor Sylvester, and the other graduate students in the DD group for all the invaluable support. And I also like to thank Mr. Tony Wang for the generous financial support and Mr. Stern for the guidance. Okay, that's my presentation. Thanks. Thank you for listening. Thanks.